So once we have an understanding of how a whole range of organic molecules react and how their functional groups can be changed, we can look at how we can produce specific organic molecules via more extended pathways like this. So if we look here, this flow chart shows us all of the functional group reactions that we've analyzed so far and how we can control each of those or allow each of those to happen. So we know that we can produce a chloroalkane from an alkane by reacting the alkane with some chlorine. We can also produce chloroalkane from an alkene through an addition reaction by reacting the alkene with some hydrochloric acid. Again, alkanols can be produced from chloroalkanes via a substitution reaction. So we substitute the chlorine in the chloroalkane for a hydroxide. Or we can produce alkanols directly from alkenes by adding water across the double bond in the alkene. And lastly, the hydroxyl group in our alkanol can be substituted for an amino group to produce an amine, or it can be oxidized to produce a carboxylic acid. And obviously, from there, we can also produce esters. So this is basically a nice, clear, concise list of all of the processes that we need to know. And the key processes in sort of these basic organic molecules and how they can be produced. Now, it's an important consideration when we're designing a reaction pathway to produce a certain product is the fact that in each of these steps, byproducts will be formed. So perhaps we want to produce a specific carboxylic acid. We want to produce a very specific type of carboxylic acid. And what we're doing is we're starting off with an alkane, and we want to get to this carboxylic acid. So what we're going to do is we're going to go through each of these steps. We're probably going to take this path. So we're probably going to go to a chloroalkane, then an alkanol, then a carboxylic acid. Well, when we turn our alkane into a chloroalkane by reacting the alkane with chlorine, then there's going to be one specific chloroalkane that we want. Say we want to produce ethanoic acid, then the chloroalkane that we want is going to look like this. We want just a simple ethane molecule, however, with one hydrogen atom substituted for a chlorine atom. So this is one type of chloroalkane. However, when we're reacting ethane with chlorine to produce this chloroalkane here, we're going to get other byproducts. We're going to get some products that look like this, for example. Perhaps we'll get two chlorines, one on each carbon atom, or perhaps we'll in fact get two chlorines on one atom and one chlorine on the other carbon atom. And so there's going to be lots of different ways that the chlorines substitute themselves onto the ethane molecule, and because of that we're going to get lots and lots of different chloroalkanes produced. And so if we are in fact following this pathway and trying to produce ethanoic acid from ethane, then what we're going to have to do is we're going to have to be able to separate those byproducts during this process. So in our first step, if we want to produce just our basic chloroalkane with one chlorine atom, then we're going to have to somehow separate that chloroalkane that we want from all of the other chloroalkanes that have been produced in this reaction. And so not only do we have to consider the actual processes that we're using to produce our carboxylic acid in the end, but we have to think about and consider the byproducts that will be formed, or the products that will be formed in these reactions, which are different to the ones that we are actually after. So what we need a way to separate our unwanted byproducts. And so probably the most common one of those is fractional distillation, and we'll go through how that works in another video. But fractional distillation is a very useful way for us to separate, for example, our different chloroalkanes so that we can get the one that we want. So when it comes to actually designing an organic pathway, we need to, basically this chart has everything that we need. So as an example, we are going to draw a flow chart for the production of an ester. We're going to draw a flow chart for the production of propyl ethanoate. So this flowchart is going to be, we're going to start with propane and ethene. So we've still got this flowchart listed up here, and we want to produce propyl ethanoate from propane and ethene. Well, we know that propyl ethanoate is produced from propanol and ethanoic acid. So the way that this is going to work is that we are going to use our propane to get to propanol, and we're going to use our ethene to get to ethanoic acid. So first we'll deal with the ethanoic acid. So we could produce ethanoic acid two different ways from ethene. We could turn ethene into chloroethene and then into ethanol and then into ethanoic acid, or we could go straight from ethene to ethanol and then ethanoic acid. So that's the way that we'll do it. So we start off with ethene here, and we know that we're doing this at high temperature with a phosphoric acid catalyst to produce, so we're reacting the ethene with the water, and the phosphoric acid is the catalyst, and so from that we're producing ethanol, and then we're oxidizing the ethanol. We could use oxygen to oxidize, or we could use other oxidants such as chromium or permanganate to oxidize our ethanol to ethanoic acid. As for our propane, we're starting with propane. We're using that by reacting it with chlorine to produce chloropropane. Now obviously we want to produce propan-1-ol. So what we want to produce, we're going to produce lots of different chloroalkanes in this reaction, but the one that we want is going to be 1-chloropropane. So that's setting ourselves up to produce a primary alcohol. And from there, the only alcohol that can be produced from 1-chloropropane is in fact propan-1-ol, because we're substituting the chlorine on the end carbon for a hydroxyl group on that end carbon. So we do this by reacting 1-chloropropane with hydroxide, and then we get propan-1-ol. And then it's simply a matter of combining our ethanoic acid with our propan-1-ol in an esterification reaction. So we know that esterification reactions use a sulfuric acid catalyst. And from there we can produce our propyl ethanoate. So it's quite a straightforward process designing these sort of reaction pathways. We simply need to apply our understanding of all of the different reactions of all of our different organic molecules and how these functional groups can be changed. And we basically just develop a sequence of these reactions in order to produce the product that we want. And so obviously it's very important to consider the fact that in some of these reactions there is more than one possible product that's going to be produced, and if we want one specific product out of those possible products, then we have to understand that we're going to need to separate that product that we want from all of the products before we use it. So that is how we look at organic pathways, and that's how we develop our own organic pathway to produce a specific desired product.